Okay, so we're talking about linear measurement. And anytime you're talking about linear measurement, it is always first degree, meaning the exponent will always be a 1. Think of it as we're measuring length. Okay? So there's a lot of ways you can do this with students. Sometimes if you use paper clips, you can use hand measurements. How wide is this piece of paper? By how many hands that you go? You can always grab, pins, and you can ask, okay, guys, boys and girls, estimate how wide this piece of paper or this board is, using whatever tools they might have around. It doesn't always have to be a ruler. So you can measure the height of a horse at its withers by hands. A hand measurement is approximately 4 inches. You can measure the height of a tennis net using a racket and the face of the racket. So there's a lot of ways that you could have them estimate their measurement. So when we're talking about measuring, we want to first look at the basic units of measure. And for our first conversion, I'm going to put it over here so we can refer back to it. English unit of measure. What you and I use for measuring in our system. Okay? We want to take a look at what we mean by a conversion factor. A conversion factor or conversion units, a conversion chart, is thinking about what are equivalent. So for example, we know in our measurements 12 inches is the same as 1 foot. 3 feet is exactly the same as 1 unit that we call a yard. And then, not sure whether you know how many yards are in a mile, but there are 1,760 yards in 1 mile. Or some people are more familiar with 5,280 feet in a mile. So here's our units of measure for our English system, the system here in the United States. So we're going to practice that first of all. All of these represent the same unit, 1 unit. And that's our key. Similar to what we did chapters ago with fractions, let's think of it this way. A unit of measure. 1 unit. This is the same as a conversion rate or ratio. A rate, okay, is a comparison of 2 fractions. So we can also think of it as a ratio or 1 fraction. So for example, 12 inches we know is the same as 1 foot. So this is considered 1 unit because they're both the same. We could say the same thing. 3 feet is the same as 1 yard. It's still 1 unit. We're just measuring it in either feet or yards. Similarly, we could say 5,280 feet is the same as 1 mile. So therefore, it's still a single unit of measurement. Okay? So how do we use this? Well, let's do a little conversion. Let's convert the following. Let's convert 30 feet, and you ask, well, how many inches are in 30 feet? Some of you may already know the answer because of shortcuts, but when in doubt, we always need to work it out so we can show students where and how come it works. So always start with your given. Always start with what you know. We're given 30 feet. I want to convert feet to inches, so I need to use the conversion fact that there are 12 inches for every 1 foot. So I'm simply going to multiply this by the unit 1 unit. Since I want to eliminate feet, and feet is in the numerator here, I'm going to put 1 foot. Since I want it in terms of inches, I'm going to put its equivalent of 12 inches. Now you'll notice feet reduced with feet, and we we are left with 30 times 12, and therefore, sorry, got distracted by our puppy here. Therefore, we are left with whatever 30 times 12 is, so this would be 360 inches. Okay? So let's do that again. Let's say I give you 288 inches, and I would like to know how many yards this is. Well, I'm going to do this problem two different ways. I'm going to do this problem two different ways. I'm going to set it up both ways. Because I could go from inches to feet, feet to yards. So we're going to start with what we know, 288 inches. I know that if I'm going to convert, I want to reduce the inches, so I'm going to make that into feet. So 1 foot is the same as 12 inches, but I need yards, so I'm going to multiply by the number 1 again, and I know that 3 feet is exactly the same as 1 yard. So therefore, I'll turn this into a fraction. Reduce, reduce, reduce the units of measure, reduce the units of measure. So I am left with 288 over 12 times 3, which is 36. The only units of measure left are yards. When I reduce, we end up with 8 yards. Now some of you are sitting there going, do I have to do that? Do I have to go all the way down? The answer is no. Because if I still start with 288 inches, well, I know some of you, all of you, may know exactly how many inches are in a yard. So I could have gone straight to the fact that 1 yard is the same as 36 inches. That's still 1 unit we're talking about. And if I reduce inches with inches, you'll notice if I multiply my fractions, I still end up with the fraction 288 over 36. The only measurement I have left is yards. Since it's the same ratio that we had before, we end up with the same outcome of 8 yards. So changing everything to single units tends to help and help students visualize and see why it works. All we are simply doing is multiplying by the number 1. So if I want to go, well, let's go extreme. Let's say we want to know, if I start with 2 miles, and I want to know how many inches this is. Okay? I don't think you may know how many inches, so you have a choice. You could go to yards and then feet. I'm going to work it all the way out. And say, all right, I'm starting with 2 miles. And I need to multiply it by the unit 1. So I'm going to start with, I want to cancel miles, so I'm going to say 1 mile is the same as, and you have a choice, I'm going to go straight to feet, 5,280 feet. Sorry. Then I'm going to go from feet to inches. Since I want to reduce feet, I put feet in the denominator. I want to keep inches, I put inches in the numerator. These are all 1 single unit that are equivalent. Therefore, if I reduce my miles and miles, feet and feet, whatever the product of 2 times 5,280 times 12, you'll notice the only unit of measure left is inches. and I should end up with, I believe, 126,720 inches. Okay, so that's how we can use our conversion facts, our conversion ratios, in order to convert any unit to another unit in the English system. Well, now let's take a look at the metric system. And some of you may have just gone, ugh, metric. I never understood it. It is so much easier than our English system, but I will show you the metric system two different ways. Okay? I will show it two different ways. All right, so metric, the main thing with the metric is getting the prefixes correct. With the metric system of measure, metric units, it's the same no matter what you're talking about. If you're comparing length, we use meters. If you're comparing weight or mass, we use grams. And if you're comparing volume, like liquids, we use liters. So our system is very confusing as far as we have 12 inches to 1 foot, 3 to 1, 5,280. We have all these numbers we need to remember, not to mention 16 ounces are in a pound, but 2,000 pounds make a ton. Or if we're looking at liquid measurement, 8 ounces is a cup, but 2 cups is a pint, but 2 pints is a quart, but 4 quarts is a gallon. We have all these numbers. The metric system is really quite lovely. If we start with whatever our base is, okay, so in this case, we are starting with meters because we're talking about length. And a meter is a little bit longer than a yard. It's about 39 inches, not quite. We just need to remember the prefixes. The largest prefix is kilo, so we would have kilometer or kilometer. Then we have hecta, hectometer. Then we have deca. Sometimes you see it with a C, oftentimes you see it with a K, decameter. Our smaller units, so I use lowercase when I do it, deci for decimeter, centi for centimeter, and our prefix milli for millimeter. And this is what's really lovely about using the metric system, is I'm talking about 1 unit of measure, 1 meter, okay? Well, if I go to the right of that, it takes 10 decimeters to make 1 meter. If I go to the right from meter 2 units to the right, that takes 10 centimeters to make 1 meter. Similarly, if I go 3 to the right, it's as if I've moved my decimal 3 units to the right, and so I end up with 1,000 millimeters equals 1 meter. Similarly, if I'm starting with my 1 unit of measure and I go to the left, 1 meter is the same as 0.1 decameters. If I go 2 to the left, this is the same as 1/100th, and kilometer would be 1/1000th, or 3 to the left. So that's one way to look at it in a horizontal manner. To stay consistent to what I did with English, I'm going to do metric in the same way. So I started off with 1 meter each time. So 1 meter is the same as, if I go to the right, 10 decimeters. 1 meter is the same as, if I go 2 to the right, 100 centimeters. 1 meter, if I go 3 to the right, is the same as 1,000 millimeters. Similarly, 1 meter, if I go 1 to the left, is the same as 0.1 decameter. Now, I don't want to use a D again because that could be confusing. So sometimes I use a capital D, or sometimes I use a DA to represent decameter. 1 meter is the same if I go 2 to the left as 0.01 hectometers, and 1 meter, if I go 3 to the left, is the same as 1/1000th kilometer or kilometer. So there's our conversion rates, and all we have to do is all we have to do is simply move the decimal point. So let's do a few conversions on this, and I'm going to do this 2 different ways. I'm going to do the exact same method that we just left off with by multiplying by 1 unit, and then I'll do sort of a shortcut. So let's say I ask you to convert, and we're going to stay within the same system. So if I'm starting with metric, I'm going to keep it in terms of metric. We're not going to worry about switching back and forth. There's a very nice conversion from English to metric, but we're going to stay within the same system. So let's say I ask you for 3.57 meters, and I would like you to change this to kilometers. As I told you, I'm going to do this problem 2 different ways. I'm going to do it again. 3.57 meters. How many kilometers? Okay. So the first way is exactly what we did with our English units of measure. Start with your given. 3.57 meters. And since I'm going from meters to kilometers, I need to know what my conversion fact is. So my 1 unit of measure that I'm going to use, my 1 unit, so I'm multiplying by the number 1. It's just a 1. Now remember, I want to reduce the meters. So 1 meter goes in the denominator. Since we're trying to change it to kilometers, I can see that 1 meter is the same as 0.001 kilometers. So 1 meter is exactly the same as 0.001 kilometers. And now exactly like we did before with the English unit of measure, reduce. When I reduce, I see that I have 3.57 times 0.001, and the only unit of measure that's left is kilometer. So if I move this, I end up with 0.0357 kilometers. So using the idea that we did with fractions several chapters back, we can convert by simply changing it to the number 1. Now, another shortcut, but we have to always know why it works. Another way to look at this to check your answer is simply to count from meters back to kilometers. Okay. So, since I'm starting at meters and I'm going to kilometers, I need to move my decimal 1, 2, 3 to the left. That will give me kilo. 1, 2, 3 to the left. So I simply move my decimal. I started with 3.57 meters to kilometers, meters, 1, 2, 3 to the left to get to kilometers. Take your decimal, 1, 2, 3 to the left. Insert placeholders. And I must have, I think I multiplied wrong over here, didn't I? 1, 2, 3, 1, I did. I so apologize for all of you sitting at home who grabbed your calculator. I apologize for that. I should get 0.0000357 kilometers. Sorry about that. I better do another example so you trust me. As an educator, it's rough when you make a simple arithmetic mistake on the first example. This is where I would ask you guys, give me a number. But since you're not here, let's just make up and look at another one 2 different ways. And sometimes my students would often say, well, how do you remember each of the prefixes? And so one way that you'll find is sometimes coming up with a clever little way to remember. And the way I showed my students, they tended to laugh. They tended to remember kilo, hecta, deca, and then deci, centi, milli, is think of the little phrase, King Henry died drinking chocolate milk. It always makes them chuckle and they can remember it. So King Henry died drinking chocolate milk. And of course, you can come up with another one, but if that helps you, great. So let's try another one. Let's say we're going from, how about, let's convert 6.47 hectometers, and let's convert this to centimeters. I'm going to do this 2 different ways. To justify the steps, okay, we need to go from hectometer to centimeter, and the one unit of measurement they have in common is the meter. Always go back to your base. So I'm going to start with what I know, 6.47 hectometers. So I'm going to first convert hectometers to meters. Since I want to reduce the hectometer, it goes in the denominator, and I'm going to take it to meters. So if I look at my conversion, it takes 0.01 hectometers to equal 1 meter. So 1 meter is 0.01 hectometers. Well, you'll notice hectometer reduces with hectometer. I'm sitting with meters, but I want to go to centimeters. So I need to multiply by the number 1 again. This time, I want to eliminate meters, and I want to convert meters to centimeters. Well, let's see. 1 meter is the same as 100 centimeters. And now we would be reducing out the meters. So the only unit of measure left is centimeter. 6.47 times 100 in the numerator. Only thing left in the denominators is 0.01. I forgot my calculator, but you'll notice that it's left with the units of measure of centimeters. Okay? Which, if I use mental math, this is the same as multiplying by 100 and then dividing by 1/100th. But I'm going to convert it and see if you guys get the same thing. So figure this out with your calculator. And let's see if I use a shortcut to figure it out and get the same thing. So if I use the shortcut, I'm starting at 6.47. And I am going from hectometer to centimeter. So I'm going from hecta down here to centi, to the right. I'm starting with hectometer, and I need to go 1, 2, 3, 4 to the right. So I take my decimal, and I go 1, 2, 3, 4 to the right. Insert placeholders. So I should end up with 64,700 centimeters. Which, again, I don't have my calculator handy. This would be the same as 6.47 times 100 divided by 1/100th. but dividing by a fraction is the same as multiplying by its reciprocal. So 6.47 times 100 times 100 over 1. And sure enough, I end up with the same answer, 64,700 centimeters. Or grab your calculator and go from there. Okay? So it's pretty cool. So metric is pretty much the same idea, only we're just moving decimals. Now let's talk about how we use the linear units of measure in our geometry. We're going to be looking at polygons, which are all line segments, and then we'll look at a circle, which is not made out of line segments. Okay, so we're always looking at first degree because it's one-dimensional. We're talking about length. So let's look at polygons. Well, we know what a polygon is. It's got many sides. So it's a closed figure. Okay? So if we're talking about polygon, we want to measure linear measure, we refer to this as perimeter, which is the sum of the sides. So for example, let's say I give you a pentagon. It's not regular, it's an irregular pentagon. I'm just sketching. And let's say I give you this side is 5 inches, then going clockwise, I have 4 inches. I don't know, how about 5 inches, 7 inches, and 10 inches? Well, since they're all line segments, the perimeter is found by adding up the sides. So you'll notice we have 4 inches plus 5 inches, 7 inches, 10 inches, and 5 inches. Since they're all the same unit of measure, I can call them inches. If they're not the same unit, then we would have to convert, like we just did in the previous examples. So if I add these all up, I believe looks like 31 inches. And we're finished. Okay. This leads us into a polygon, the smallest polygon we have. Now, I know if I only give you 2 points, you know how to find the distance between 2 points. But if I give you, let's take a look at collinear. So the smallest polygon we have, collinear points rather, the smallest polygon we have is a triangle. So let's think about that for a second. A triangle has 3 vertices. So what I'm going to do first is I'm going to give you collinear, means they lie on the same line. I'm going to give you 3 points, A, B, and C. Just make sure B, it doesn't really matter, but I'm going to make it not the midpoint. Okay? Now, if I have these 3 points, you can see that they're all collinear, they're all in a straight line. So line segment AB added to line segment BC, if I put those end to end, you can probably notice that that equals the line segment from A to C. If I want to talk about their measurement, I don't need the segment bar. If I want to talk about how long it is, let's pretend that AB is 8, and let's pretend that BC is 12. I don't need to put the line segment bar. If you have AB without the line segment, it means the length. If you have BC without the line segment bar, it means the measure of the length. So the measure from A to C would be 20 units long. whatever unit of measure you're using. Okay. So if they're collinear, we simply add them together. Now, let's look at what it looks like if they're not collinear. If points A, B, and C are not collinear. Okay. Then they form a triangle. So let's say I have, well, let's do it this way. Here we go. Here's A to B. Here's B to C. You may notice that, sure enough, they form a triangle, ABC. And what's really cool about this is a theorem that goes along with it. Because what it says, now remember, if they're located right next to each other on the same line and are collinear, I can add them together, and two segments add up to form the third segment. But imagine I take this and I take B and I swing it off of that line, and I put it up here. Now you may notice it's up here. So it's not going to equal AC. So we have this great triangle sum theorem, right? That says if I take any two sides, let's say I take side AB and I add it to side BC. Well, now remember, if B was located right down on here, on this collinear line, if all three of them are lined up, then that's going to equal the total distance. On a triangle, any two sides added together will always produce a number larger than the length of the third side. Or another version of this could be, let's take AB and add it to AC. AB, AC, that's got to be longer than side BC. Or let's take AC and add it to BC. That's got to be greater than and longer than side AB. So any two sides of a triangle added together will always be greater than the third side. So let's take a look at a couple of examples going along with that. Can a triangle be formed with the following side lengths? Can a triangle be formed having sides? Your first example. Let's say we have, what are nice numbers? How about 4 meters, 7 meters, 5 meters? Well, let's check it out. Now, if you're visual, and I'm not going to connect these on purpose, I'm just sort of going, well, if this is 4, this is 5, and this is 7, could those form a triangle? Let's find out. We would have to check all three conditions. So what I'm going to do is I am going to take a look at the sides, and I'm just going to go in order that they gave us, 4, 7, 5. I'm going to say, well, is 4 plus 7, since they're all the same units, I'm not going to worry about that, greater than the third side of 5? Well, the answer is yes. 11 is greater than 5. Is 4 plus 5 greater than the other side of 7? Yes. 9 is greater than 7. And lastly, is 7 plus 5 greater than the other side of being 4? And the answer is yes. So since all three scenarios work, this could be the side length of a triangle. So let's try it again. Let's say I give you, I don't know, how about 10 meters, 6 meters, and 3 meters. We have to find all three scenarios. So if this is going to be a triangle, if I take 10 plus 6, that would be greater than the other side of 3 meters. Yes, it is. I could take 10 meters and 3 meters. Sure enough, it's greater than the third side of 6 meters. But if I take 6 meters and 3 meters, is it greater than the third side of 10 meters? And the answer is clearly no. 9 is not greater than 10. Therefore, a triangle cannot be formed using those three lengths. Okay, so that's kind of an interesting triangle fact, working with the lengths of the sides of a triangle. All right. Now, how else could we use this? Well, we're going to use the same theorem, the same idea, but how, as the teacher, oftentimes, you're making up examples, you're trying to create something, and a student might say, well, what if I gave you this side and that side? Okay, so let's try to figure out how, as the teacher, you could come up with numbers or answers that will always work. So let's do this. Okay. Let's try, it's a little wet, sorry about that. Let's try the following. If two sides of a triangle are 18 centimeters and 70 centimeters. And for ease for this first example, let's make sure everything's a whole number. And the length of the third side is a whole number. And remember, a whole numbers are non-negative, so 0, 1, 2, 3, 4, etc. Of course, 0 wouldn't work, it wouldn't be a triangle. Okay, I have two questions for you. The first one is, what's the longest side that we could have for the longest measure for the third side? What is the longest, or longest, because we're talking about distance, what's the longest that the third side can be? Okay, well, let's think of it this way. I'm a visual, so I'm going to take and say, all right, I'm going to kind of draw a picture. And say, all right, here's side AB, and I know that is 18. Here's side BC, and I know that this is 70. The units are measured the same, so I'm not going to include those in my picture. I want to know how long is this side from A to C. And I want to keep in mind that we knew earlier, if you think back to when we talked about collinear, if these sides were on the same line, if here's A and here's C, and I took this point B and I put it back down on here, right? So I took B, which is up here, and I put it back on here. So here's B. Remember, we know that AB is 18 and BC is 70. So right away, the longest section we have, if we add them together, is 88. Okay, so keeping that in mind, and keeping in mind what we just learned, if I add any two sides, they must be longer than the third side. So that means if I take, this is what we know, any two sides have to be greater than the third side when added together. So if I take the length of AB, so I don't need this segment bar, plus the length of BC, I know that has to be longer than the third side. So therefore, 18 plus 70 has to be greater than AC, which means 88 has to be greater than however long the segment is. So how long can the side be if 88 is greater than it? Another way to look at this has to be less than 88. Well, what whole number is less than 88? The largest whole number less than 88 is 87. Okay. Another part, well, instead of asking for the longest side, is there a side that's the shortest side? So what's the shortest distance? What is the shortest value that the third side can be? Okay. Well, again, with the same idea, if I add up any two sides, that's to be greater than the third side. Well, in this case, here, I'm going to do it this way. Here's what I know. I know from A to B we're calling 18, and from B to C we're calling 70, and we don't know the other side. But I do know that if I add any two sides, it has to be greater than the other one. So it does not really make sense to take 70 and add it to 18, because 70 is already greater than 18. So we know that's true. But it does make sense to go the other way. So I'm going to say, okay, I know that the sum of two sides has to be greater than 70. So I know that AB plus AC has to be greater than BC. It's one of our three versions. I know AB is 18. I don't know AC, but I know it has to be greater than 70. So if I subtract 18 from both sides, I know that this has to be greater than 70 minus 18, 52. So again, in this case, what's the smallest value greater than 52 that's a whole number? Must be 53 centimeters. Okay? This should also be centimeters. So that's how we can use that triangle sides theorem. So that's what we can look at with polygons and linear measure. Now we want to take a look at circles. We're not going to go into the proof of how this came to be, but you can fit any polygon inside of a circle, any regular polygon. So let's take a look at circles. If we're talking about linear length of a circle, and some of you might go, wait a minute, how can I do linear length of a circle? There's something in pre-calculus we call the wrapping function. Wrapping, W-R-A-P. Think like wrapping paper or a roll of paper towels that starts as a circle. And imagine you cut that circle and let this side fall one way and this side fall the other way. You may end up seeing that it's going to roll out just like you would with wrapping paper, and it's going to cut and it's going to lay out like a line. So we can measure the distance around a circle in a linear manner. That distance around a circle we call circumference. We cannot call it perimeter because we don't have side lengths to add up. And again, easiest way is think of wrapping paper. When you unroll the wrapping paper, it unrolls and it forms a line on your counter to wrap your present. So the formula for circumference is 2 times pi times the radius. And in this case, since we're talking about length, we can use that pi is approximately 22 divided by 7, or approximately 3.14. Okay, physics, calculus, pre-calc, we can use pi as an angle measure, but we're not doing that today. We're just looking at it as length. All right. So for example, let's take a look at a couple of these. Find the circumference of a circle having radius 4 inches. Well, again, all course long, I've always talked about start with what you know, start with what you're given. Now that we've done proofs, always start with what you're given. We are given circumference, so I know, and I start with the fact that circumference equals 2 pi r. Since we're asked to find the circumference, 2 is a constant number, pi is a constant number, and the radius in this case is the number 4 inches. Now substitute in what we know. We know that this is 2. We know that we are supposed to use 3.14 for the constant number pi times 4 inches. You'll notice there's only one unit of measure, and inches is to the first degree. Therefore, I know its length. And that gives us a final value of, estimated value of 25.12 inches if you use a calculator, or an exact value if you don't use a calculator. 2 times 4 is 8, so we're left with 8 pi. Okay, so pay attention to the directions as to which version you're going to be asked for. Now we could go the other way and say, all right, let's do this. I would like you this time to find the diameter of the circle. And this time I'm going to tell you that the circumference, what's a good number? How about, let's see, circumference is 36 pi. And our unit of measure will be centimeters. Well, again, let's start with what we know. We know that circumference, if I annotate, circumference is 2 pi r. This time I gave you parts and pieces. I gave you the circumference is 36 pi centimeters. So I know that's the same as 2 pi r. Since we're solving for the radius, the diameter, okay, we'll come back. Let's first solve for the radius. We'll divide out the 2 and the pi. We'll divide out the 2 and the pi. 36 divided by 2 is 18. Pi reduces with pi. So you'll notice we are left with a radius of 18 centimeters. But to refresh your memory, if you have a circle and the radius is the shortest distance from the center to a point on the circle, that means the shortest distance from a center to a point exactly opposite that is another radius, and that's what we call a diameter. So the diameter equals 2 radii. Therefore, in our problem, since we know the radius is 18, the diameter would equal 2 times 18 centimeters. Our final answer for our diameter is 36 centimeters. So some of you may have gone, well, wait a minute, that's almost identical to what we started with. And the answer to that is yes. Since we know that the diameter is 2 radii, and our equation has 2 radii, another version of circumference, since 2 radii make up a diameter, you could have said the diameter times pi. Yes, I did that on purpose. Came back full circle. Haha. And the very last thing I want to take a look at is, well, what if you only have part of a circle? We talked about arc length a couple of chapters ago, and let's say we want to measure and find actual how long is the arc length. Instead of comparing it to the central angle in degrees, we want to find the actual measurement of an arc. Let's take a look at that. All right, so let's take a look at our last topic for this section, and that is going to be how to find the measure of an arc. So let's arc length of a circle. Now, some of you will memorize a formula. Others are starting to analyze. So let's think about this for a second. If I give you a circle, and on this circle, I give you, here's a radius, here's the same radius because it's the same circle, and I give you some angle measure, some central angle that I call theta. This is the Greek letter theta. It's just the central angle. Okay? But I'm asking you to find this arc length. So that this time I want you, I know the degree is going to be the same as the central measure, but that's not what I'm asking. I'm asking you to lay this out and measure it and tell me how long it is. Okay, tell me the linear measurement. Well, you'll notice that that arc length is only part of a circle. So what I'm going to do is I'm going to write that out in words. This is part of the circumference. Circumference, sorry. So part, well, what part? You'll notice that this is only a piece of the circle, so you could think of this as the fraction. What fraction of circumference, which is 2 pi r? What fraction are we talking about? Well, notice they gave us a central angle. And how many degrees, or what's the angle? How many degrees are in a circle? There are 360 degrees in any circle. So what fraction of the circle are we talking about? We're talking about what piece out of this 360 degrees are we looking for? Of means multiplication, circumference, 2 pi r. And that's how we can find the arc length that your author refers to as L. Okay? So it's just a fraction of the circle. It's a portion of the circle. So let's say, for example, I give you a circle of radius 5. My circle's a little off. My angle, I had to enlarge it so it's not accurate at all, but I wanted you to be able to see it's a 30-degree wedge. And my question to you is, how long, if I could take a measuring tape and I could stretch it along that arc, how long is that length of the arc? So start with what you're given. Start with what you know. You know arc length is always a fraction of the complete circumference, 2 pi r. Well, the question is, what part of the circle did I give you? I gave you the wedge that was cut out by a 30-degree portion. So I gave you a 30-degree out of 360 degrees, and I gave you a radius of 5. And in this case, I didn't give you units, so we would just call it units. So reduce, this will, degrees reduces with degrees, so I'm left with 1/12. 2 times 5 is 10. So reduce 10 and 12 by 2, so I get 5 pi over 6 units, because I did not tell you what unit of measure to use. So it's just a fraction of a circle. Since we're talking about the distance around, I just want the fraction around the circle. Okay. And lastly, what if I give you the other way? So this time, the radius of a circle, I'm going to give you the radius. Of course, the symbol for a circle is a circle. The radius of a circle having a central angle 87 degrees and an arc length of 154 centimeters. Okay, the radius of a circle having a central angle of 87 and an arc length of 154 has, so find, let's see, the only thing I guess I forgot to put find at the very beginning. Sorry. Find the radius of a circle having. So I was all right at the beginning. I didn't pay attention to my grammar. I apologize for that. So let's put the directions up here of find. There we go. Find the radius of a circle having. Sorry, you just erased twice. Okay. Now, some prefer a picture, so this time I'm going to draw a picture. Start with what I know. I don't know the radius this time. I don't know the radius, but I know the central angle is 87. And this time I know this length, if I were able to measure it with a measuring tape, is 154 centimeters. Find the radius. Or I could start with the formula. I know that to find arc length, I know the arc length is a fraction of the entire circumference. So if I substitute in what I'm given an arc length of 154 centimeters. I'm given an angle measure of 87 degrees out of 360. 2 is a constant, pi is a constant, and I don't know the radius. So if I cross multiply first, I have 154 centimeters times 360, because notice my degrees reduce, equals 87 times 2 pi times the radius. Well, since I'm solving for the radius, I'm going to divide both sides by 87 times 2 pi. So I'm left with a radius. Notice on the left side, there's a unit of measurement of centimeters. So I have 154 times 360 divided by, what is that, 160, 174 pi? If I let the calculator do the work, I end up with, I believe, right at 101.47 centimeters. Okay, and so there you go. So you have circumference, or in this case, arc length, which is part of the circumference. So I hope that helps you guys. We'll tune in next time for 14.2.